So yeah. So here are a few techniques. The first one, I called them all fun things. So I call this one superposition. Don't ask me why.
It was late.
It was late. So
That's your new catchphrase?
I don't know. So in hand, meaning this is what we've got, right? This is given. We have outputs y1 and y2 of an ODE for inputs u1 and u2, okay? In the bush, meaning, you guys know the saying, right? Okay, so we don't have it, so we need it. The output, y3, for input u3 equals a linear combination of those two inputs for constants a and b. So we're sort of boiling this down a little bit. So our MO here, our method of operation, modus operandi, which is the better way of saying that. Didn't want to go all Latin on people. Is to use superposition. So y3 is just equal to the linear combination of y1 and y2 in the same way it was combined with the inputs. So note this works for scaling a single input too. So if you scale the single input by a, you get the output scaled by a. Okay? So that is just, I kind of like boiled it down. I don't know. I just felt like maybe this would be helpful. Here's another shortcut. Calculation. So say you have output y1 for an ODE that had an input u1. In the bush, what you want is output y2 or y3 for input u2 being the derivative of the original input, or u3 being the integral of the original input. So this is why it's calculation, because it's calculus we're using. Yeah. Okay. So use the derivative integral rule. So y2 is the time derivative if it was a time derivative of the input, and it's the integral if it's the integral of the input. Calculation. All right. Here is snoozation. We have an output, so what we would like, or so we have already an output y1 of ODE for input u1. In the bush, we literally want y1. Literally y1. So our MO here is output y1 is in a table, like table 9.2 for first order systems or table 9.3 for second order systems. And you read it. Good for you. Good for you. Okay. I put this in there because this is literally how we solve some of these. It's a shortcut, and I want to make sure that we do. And it's snooze itching because it's super easy. You don't hardly have to do anything, just to read it. Okay. And then shortcut 4, which I had to get a little bit creative, was mixing in the initial condition.
So contrived. That was a force function. It was force
Sounded like a forced response to me.
It did.
So, in hand is the output y1 for of an ODE for input u1 with no initial conditions. Okay? But I want, so in the bush is output y2 for input u1, same input, but with non-zero initial conditions. Okay? So what we have is the output for a certain input with no initial conditions. So we have a forced response, but we don't have the response for that same input and some initial conditions. So what do we do? So this happens a lot because Snoozichin tables are a thing. They're always computed for zero initial conditions, those tables. So they don't compute them for non-zero initial conditions, they compute them for zero initial conditions. But now you have initial conditions. What are you going to do? Throw up your hands and just say, can't do it. When your input matches the table, but the initial conditions are non-zero, you can use the result from superposition that you can add the forced response to an initial condition response to get the output, right? So, YF can often be found from tables, but there are typically no tables for YIC. We don't have tables in the book, for instance, for YIC. It is found from homogeneous solution of Y with the initial conditions applied. Although the text doesn't tabulate YIC, it does solve for Y homogeneous for first and second order systems. So for first and second order systems, you can look through the section and find homogeneous solutions in there, which is going to be helpful, as we'll see in a moment. Here's the algorithm. So it doesn't tabulate YIC, but it does give you the homogeneous solution, which is just very close to YIC, right? All we have to do is apply the initial condition to the homogeneous solution. So here's the algorithm, because I felt like it's kind of useful to have a solution algorithm. So the first thing to do is find YIC, because we know we're just going to have to find YIC, add to YF to get the full result down in 3. So we need to find YIC. So how to do that? Find the homogeneous solution, YH. How to find the homogeneous solution? We can either use a typical method of finding the homogeneous solution, which is pretty straightforward, characteristic equation, et cetera, or we can look it up, because maybe it's a first or second order system, and chapter 9's got it in there on page whatever. Okay, so those are our options. And then we apply the initial conditions that we have to Y homogeneous. Okay. Step 2, find the force solution. So first thing we could do, if it's available, look it up in a table. Or if we don't have that, we would use the method of undetermined coefficients, which would go through this process. So find the homogeneous solution. You should already have it from up here. Be careful not to use YIC, because YIC already has the initial condition applied. So don't use YIC. Use the homogeneous solution. Then find the particular solution using your method of undetermined coefficients as usual. Add them up and apply the initial conditions. Find YF by applying the initial conditions all set to 0, right? Because we're finding the forced solution, so all the initial conditions should be 0. So do that. And then finally add YIC and YF together to get the full response. Obviously, this method is only easier if you already have Y homogeneous and possibly Y forced from a table or somewhere. You got to have that. Otherwise, just solve it using the usual method of undetermined coefficients from the beginning, right? So if you've got some already solved for you, then use this method. But if you don't, then you just can start over from the beginning and roll your own, which is sometimes just preferable anyways. All right, guys. I will see you Friday.